In this video, we're going to look at section 1.4, which is on inequalities and interval notation. An inequality occurs when it is possible that two algebraic expressions are not equal. So with numbers, something that's always true is if A does not equal B, if the numbers are not the same, then either A is less than B or A is greater than B. And so we have symbols to represent these phrases because we don't have to write these phrases over and over again in words. So is less than is represented with this symbol here, right, the symbol that you see right here, and is greater than is represented with this symbol here. So whenever you see these symbols, that's how you translate them back into words. So here this says A is less than B, this says A is greater than B. All right. If you see a line underneath the symbol, like you see here, there's this line right here, that indicates that equality is also a possibility. So this symbol would be read as less than or equal to, and this symbol here would be read as greater than or equal to. And we'll see that in some of the problems as we go forward. A solution to an inequality, just like with an equation, is any value that when substituted for the variable results in a true statement. So if we can take a number and plug it in and get something true, we call that thing a solution. And so the first problem you're going to have on your homework is about this topic. So we have this inequality over here. So I'm going to write it out again. We have x minus 1 is greater than or equal to 6. And then we have this list of numbers right here. And what they want us to do is go through each one and determine if that number is a solution to the inequality. So in a problem like this, what we're supposed to do is take the number, plug it in, see if it comes out true or false. So let's go ahead and start with -2. We'll plug that in for x. So we're going to get -2 here in place of x. Minus 1 is greater than or equal to 6. We combine this together and we get -3 is greater than or equal to 6. And so -3 is actually not greater than 6. -3 is smaller than 6. And so this would be false. And so -2 is not a solution to this inequality. All right. If you're having trouble telling if which number is bigger or smaller, you could consider the real number line, which is something we are going to be using in some problems later on. So let me just go ahead and introduce it now. So this is the real number line. Every number that exists, except for imaginary numbers, but every real number that exists somewhere on this particular line, and they're in numerical order. And so we have 0 somewhere on this line, and so I usually put that in the middle. Negative numbers are to the left, positive numbers are to the right. Numbers are smaller if they're further to the left, they're bigger if they're further to the right. And so if we put these two numbers on the real number line, -3 would have to be to the left of 0, it'd be over here. +6 would have to be to the right of 0. And again, smaller numbers are to the left, bigger numbers are to the right, so -3 is smaller than 6, whereas this symbol says greater than, so that's why it's false. I don't want to go through and check every one of these numbers because it gets a little bit repetitive, but let's do one more. Let's go ahead and look at the last one. So we'll do 20. So we do the same thing. We have x minus 1, so we're resetting. We go back to having x here, and in place of x, we're going to plug in the number 20. And so I'll have 20 minus 1 is greater than or equal to 6. We simplify. 20 minus 1 is 19. 19 is greater than or equal to 6. That is true. So again, if you look at the real number line, 19 would be kind of a ways down here. 19 is further to the right than 6 on the real number line, so 19 is bigger than 6. And that's what the symbol says. 19 is bigger than 6. So this is true. And so therefore, 20 is a solution to the inequality. All right, so that's how you'll determine which numbers are solutions and which ones are not solutions. And then I think what you do is you take all the numbers that are solutions and type them in on a list. This particular one, if we just look real quick with these other two numbers, 0 will not be a solution because you'll get -1 is greater than 6, which is not true. And 6 actually will not be a solution because 6 minus 1 gives you 5, which will not be greater than 6. And so, in fact, the only solution in this list is the number 20. All right, whoops, went too far. All right, so let's consider a couple of these inequalities here. So these aren't really homework problems, but just I want to talk about some concepts. So if I ask you what are the solutions to this inequality, what numbers will make this inequality true, hopefully you start with numbers like 0, 1, 2, 3, I don't know, I guess you could, it doesn't really matter where you start, but what you should realize is that you won't run out of numbers, right? So we might start with 0, for example. So is 0 a solution? Well, let's plug in 0 for x. 0 is greater than negative 2. That's true. 0 is bigger than negative 2. It's further to the right on the real number line. If we plug in 1, 1 is bigger than negative 2, so that one's true. So 1 is a solution. 2 is a solution. Negative 1 is bigger than negative 2. That's a solution. And we could keep going. 3 is a solution, 4 is a solution, and I'm actually skipping over a bunch of numbers. We don't usually think about them, but numbers like 1.5, 1/2, pi, right? Pi, 3.14, etc., is a solution to this inequality. There's an infinite number of them. So what we usually try to do, so the way I think of it is, our preferences. So our preference would be to list the solutions. That's our first preference. That's our primary preference, and that's what we do when we solve equations, right? So when we were solving equations earlier in the chapter, we got a solution for the equation like x equals 5, and we said the solution is x equals 5. We listed it because there was just one of them. If we got two solutions, which we haven't seen yet, but if we did happen to get two solutions, we would just list the two solutions. So listing is our first preference. But that's not going to be possible here because there's just too many. This list is just going to keep going. I can't possibly list all the solutions to this inequality. So whenever that happens, because it happens in a couple of different circumstances, we instead draw a picture of the solution. So that's our second preference. So if our first preference is not available, if we can't list all the solutions, then our second preference is going to be to draw a picture of where the solutions are located in some visual way. And we're going to be doing that here with these inequalities on a real number line. So we'll draw a real number line. We'll try to make it a line. All right. So just like we had before, we have 0 here. And let's find these numbers on this real number line. We have 0 itself. That's a solution. We have 1. That's a solution. We have 2. That's a solution. And you'll find that they all kind of exist in a big group in one particular spot on the real number. I shouldn't say a spot, but in one region. That's a better word there. So all the solutions are going to be kind of grouped together in one particular region on the real number line, and it's our job to find where that region is located. Pi would be 3.14. It's a little bit further down here, and any numbers to the right will continue to be solutions. 4, 5, 6, those are all solutions to this inequality, and so they all exist over here. So we see that they're all kind of clumping together collectively over here in this region right here. So it seems like every number in this region happens to be a solution and will continue to be solutions as we go to the right. So we kind of shade in the arrow as well to say it's just going to keep going that way. All the solutions, all the numbers in this direction will be solutions to this inequality. But going to the left, we'll run into some trouble. So for example, negative 3 is not a solution, right? That doesn't work out. Negative 3 is not bigger than negative 2. It's smaller. And so there's going to be a limit to how far to the left we're going to be able to go and still find solutions. So the furthest we're going to be able to go to the left is the number negative 2, because negative 2 works only because of the equals 2. Right? Negative 2 is equal to negative 2. So that also would be a solution, and then that's where it stops. Right? Negative 2.1 is not a solution, right? Because negative 2.1 is not bigger than negative 2. And so that's as far to the left as the solutions are going to go. And so this would be our graph, right? So we have visualized the solution set to this inequality on a real number line, since we couldn't list all the solutions because there's too many. Let's think about this one. So here, and so you might say, is this what I have to do on the homework to find the solutions? You shouldn't have to go through this level of detail. I'm going to show you what to do over here, but what I normally do is I draw the real number line, find this number on the real number line, which is right here, right here, and then I decide which region to shade in. It'll either be to the left of that number or to the right of that number. And so in this case, we're shading to the right of the number -2. And so that's what we're going to do here. So let's, instead of listing specific solutions, let's just jump to the end of the reasoning that we're doing over here and just find where all the solutions are located all at once. So here's the real number line. Here's 0. Now 3 is a pivotal number here. That's going to be sort of our cutoff value, right? It's going to be the endpoint to our solution set. So I'm going to go ahead and find that on the real number line, and then try to determine where the solutions are located relative to the number 3. And so this inequality is looking for numbers that are less than 3. And so here's 3. The numbers that are less than 3 will be to the left of 3. Right? So it'll be these numbers here. Right? So I'm not going to go through and list 2 and 1 and 0. I'm just going to visually find it on the real number line. Find the number 3 first, and then in this case we're going to shade to the left of 3 because that's where the numbers get smaller than 3. And so this will be my solution set here. But this one has a twist, because the number 3 itself is not a solution to this inequality, right? If we plugged in 3 for x, we get 3 is less than 3, which is not true. 3 is not less than 3. 3 is equal to 3. And so 3 itself is not a solution. So you might say, well, then maybe I shouldn't have started at 3. Maybe I should have started at 2. But then you're leaving out numbers that are solutions, right? We don't want to leave these numbers out, like 2.1, right? 2.1 is less than 3. That is a solution. That needs to be here. 2.9 is less than 3. That's a solution. We need to make sure to shade that number in. 2.99999 is less than 3. And so that needs to be a solution. So we can't start at 2. We still have to start our graph at 3, but we want to indicate that 3 is not part of the solution set. Whereas here, -2 is part of the solution set, and so we need notation to indicate whether we're including these numbers or not. And so the old school way of doing this, the way you probably learned it, seems like it's still taught this way, is to use an open circle or a closed circle. So in this case, for -2, to include that number in the solution set, we use a closed circle. And here for 3, to not include the 3 in the solution set, we use an open circle. So that would have been, and that's fine, that's still used, but in this course, in this textbook, we're going to use different notation. So instead of using closed circle, open circle, we're going to use brackets or parentheses. So to include the number in the solution set, when there's an equals to, we will use a bracket. And you face the bracket towards the direction that you're shading in. So we're going to face this bracket to the right. And when we don't want to include a number, we use a parentheses. Oh, maybe I should try that again. Let's undo that. Okay. Try that again. Okay, that's a little bit better. Ugh. Okay, so we use a parentheses to show 3 is not being included here. And there's a good reason why we're using different notation. We'll see here in just a second. All right, so this would be a good way of expressing the solution set to an inequality when there's an infinite number of solutions. Drawing a picture of where the solutions are located on a real number line. All right. Another way, however, and this isn't always an option, but it happens to work for inequalities, it's not something we'll be able to use later for different topics, is interval notation. So this is the way interval notation works. So if you see a comma b with parentheses around the a and the b, like you see right here, this notation means all the numbers between a and b. So it looks like an ordered pair, right? So if you saw something like this, 1, 5, you think, oh, that's the point 1, 5. Not in this section. In this section, this is not the point 1, 5. This is the set of numbers between 1 and 5. It would be these numbers here. Right, here's 1, here's 5, of course here's 0 right here. I'm talking about these numbers right here between 1 and 5. So 2, 3, 4, 1.1, 1.2, all the decimals and fractions and all that. Now, this does not include the endpoints. This does not include the numbers 1 and 5. So this is all the numbers between 1 and 5, not including 1, not including 5. If we want to include the 1 or the 5, we have to use a bracket. So if we have a comma b with brackets on the a and the b, this would mean all the numbers between a and b, including a and including b. So we would be including both of the endpoints in that case. Sometimes you might want to include one but not the other, and so you can mix and match, right? So here we're including the A but not including the B. So this is all the numbers between A and B, including A but not including B. And this is all the numbers between A and B, not including A but including B. All right. So use a bracket to show you're including the number, a parentheses to show that you're leaving the number out. And that's why we're using that notation in our graphs as well. That way it's consistent. It's the same in both, right? We're using the same notation in graphs and in intervals to indicate which numbers get included and which ones get left out. All right, so let's go back to this problem and write this solution set using interval notation. I guess the other thing I should say, and I don't see it here. Do I have it on the next screen? I don't. Okay, there's another important detail I left out, which is that this has to go from smallest to largest. So writing this as 5, 1 doesn't make sense for interval notation. It's an invalid format for it. So it has to go smallest to largest. So I should write that here. So A has to be the smallest number in your region, in your interval of numbers, and B has to be the largest number in your interval of numbers. Right, it has to go smallest to largest. All right, so going back to this, if we wanted to write this solution set in interval notation, we would go from smallest to largest, which means from the very left to the very right. Right, the smallest number is the number furthest to the left, the largest number is the number furthest to the right. So going from smallest to largest, the smallest number in this region I have shaded in is -2. So that's what would have to go first in my interval notation. And this is kind of a trick question. The largest number in my shaded region, there isn't one. So the right answer, now you may know what we're going to put here, but the correct answer to this is there is no largest number because it just keeps going. Right? 5 isn't the largest number in my shaded region because 6 is also there. 1,000,000 is not the largest number in my shaded region because 1,000,000,000 is also a solution. Right? So it just keeps going forever to the right. So we have a symbol in mathematics to represent that situation where something just keeps going forever without stopping. It's the infinity symbol. Right? And so that's what we're going to have to use in our interval notation to indicate that there really isn't a largest number. It keeps going forever to the right. So we're going to use infinity here. We use a bracket on the -2 to show we're including the -2, just like we did in our graph. And all of this is because of the equal sign in our inequality. But with infinity, this is an important rule you need to know because it'll get counted wrong on the homework if you do the wrong thing here. Infinity always has a parentheses every time. Right? If I could draw parentheses. Oh, I hit the wrong button. Okay, I gotta go back. So let's try that again. I'm not happy with that parentheses. Let me erase that. We'll try this again. All right, so infinity. Apologies, I'm still learning the software. All right, so there's infinity, and there's a parenthesis. Okay, that looks better. And so that's writing the same set of numbers in interval notation. This is all the numbers between -2 and infinity. Here we've shaded in all the numbers between -2 and infinity. And the solution to this inequality is all the numbers bigger than -2, all the way up to infinity. Right? So we're talking about the same set of numbers in all three of these expressions. All right, let's do the same thing here. Let's write this in interval notation. Again, we have to go smallest to largest, which means from the very left to the very right. So we don't start with 3 this time. It's a very common mistake. I'll get students that do 3, -infinity here, and that is incorrect interval notation. That's going largest to smallest. You have to go smallest to largest. The smallest number in this region is, there isn't one. It keeps going forever to the left, so we're going to use the infinity symbol here. But because we're going to infinity in the negative direction, we give this a slightly different symbol. We call this negative infinity. So the number furthest to the left, the smallest number in my region, is negative infinity. We always put parentheses on infinity. And the number furthest to the right, the largest number in my region, is 3. And so that's what I'll put here. And then we have parentheses on the 3 just like we have in our graph. Because there is no equals to here, we're not including the 3 in our solution set. And that's what the parentheses is there to indicate. And so this would be the interval notation for this solution set. All right, so that's how you graph, and that's how you do interval notation. So let's take a look at some more generic inequalities. I guess we'll do here in just a second. Looks like we have one more. Maybe this will be a good one for you to practice. So if you're watching this video, if you want to pause for the moment, try to write this in interval notation. I would recommend first graphing it, and then from the graph you should be able to figure out what the interval notation looks like, and then see if you come up with the same answer that I'm about to write down. All right, so I would graph this first, even though it doesn't ask me to graph. For me, having a visual to look at helps me figure out the answer. So I always put 0 on my real number line, and then we have -2, which will be to the left, pretty close to 0, and then we have -10, which will be further away from 0 to the left, right? Because they're both negative, they have to both be to the left of 0. And then we want the numbers between -2 and -10. That's what this inequality is indicating. We want numbers that are less than -2 but bigger than -10, right? Greater than -10 but less than -2. And that's going to be the numbers between -10 and -2. So these numbers right here. All right. And then you have to ask yourself, do I use parentheses or do I use brackets on these endpoints? And because there's no equals to here, we will use parentheses on both of them because they both are missing the equals to. And so that's what the graph looks like. And then from this graph, the interval just kind of falls right out of that. You just go from the very left to the very right. So we're going to go from -10, comma, to -2. Use the same notation that's in the graph. Parentheses on the -10, parentheses on the -2. And that's writing that solution set in interval notation. All right, so now we're going to look at, I jumped ahead of myself a little bit earlier. Now we're going to look at some more general inequalities, but ultimately they all come down to problems that look like this, like these problems here. I'm sorry, I kind of marked up on them, but so we'll start off with something a little more complicated, but what we're going to do is solve it for x, and once we solve it for x, we'll get inequalities that look just like this. So every problem is going to boil down to an inequality that looks like this or looks like this. And then from there, we get the solution set by graphing and writing it as an interval. Right? To solve it for x, we're going to solve it the same way we would solve a linear equation, just like we were doing earlier in the chapter. Get x by itself on one side. Right? We're going to isolate x to one side of the equation, and that's how we're going to solve these inequalities. Following the same process, adding and subtracting the same thing to both sides, multiplying or dividing the same thing to both sides. But there is an additional rule that you have to keep in mind as you're doing these inequalities, which is that if you multiply or divide by a negative number on both sides of the inequality, you have to flip the symbol around. A lot of people like to say you change the sign. I kind of think that's a little too ambiguous. I like to be a little more specific. So you flip the inequality symbol around if you multiply or divide by a negative on both sides. Now this rule is not invented just to give algebra students a hard time and hope that they make mistakes and forget to do something that we tell them to do. This is just how numbers work. And so I'm going to show you why this rule has to be enforced. Not using algebra, just using numbers. Right? So if I have 1 and if I have 2, right? If I put these two numbers down on the screen, I have 1 and 2. What symbol do I put here in between them to make this a true statement? 1 is, let me use a different color, 1 is less than 2. So that makes it a true statement. And if it's a true statement, I should be able to change it in whatever way I want, as long as I do the same thing to both sides of the inequality and balance it out. So what I'm going to do is divide by a -1 on both sides, just for fun. All right, that's balanced. So when I do that, I should get something that's still true, right? So 1 divided by -1 will be -1. 2 divided by -1 is -2. And for this statement to remain true, which it should, what symbol will I have to put between them? -1 is now greater than -2. So it's just how numbers work. If you divide by a negative number, it changes which one's bigger and which one's smaller. They switch. And so we have to flip the symbol around to reflect that. With numbers, you can actually evaluate it and see that that has to be done. When you have variables, it's harder to see. And so you're going to have to do a good job of remembering to do this, because nothing's going to jump out at you to remind you. You're just going to have to make sure you remember. If I divide by a negative on both sides, flip the symbol around. Or if you multiply by a negative on both sides, you flip the symbol around. Excuse me. All right, so let's take a look at this problem. We have 6x plus 8 is less than 56. All right, so we want to find the solution set to this inequality. But before we try to figure that out, we're not going to try to guess, well, maybe it's the numbers that are bigger than 5 or whatever. We're going to get this inequality to tell us what numbers make this inequality true by solving it for x. Right, so I want to get x by itself on one side of the inequality. I will do this exactly the same way I would for solving an equation. So if this was an equation, what would I do first? I would subtract 8 from both sides. So I'm going to do the same thing for this inequality. Right, the 8's cancel out. I get 6x on the left hand side. 56 minus 8 would be 48 on the right hand side. And when we subtract on both sides, we do not flip the symbol around. It's only if you multiply or divide by a negative number. We're not multiplying or dividing here, so this does not get flipped around the other way. It stays less than. And then we divide by 6 to get x by itself. So just like I would if it was an equation, divide by 6 on both sides. And I'm going to get x on the left hand side because the 6's are going to cancel out. And I'll get 48 divided by 6, which will be 8 on the right hand side. And again, I do not flip the symbol around because I didn't divide by a negative number. I divided by positive 6, and so this will still be a less than. And so that's solving it for x. And so over here, we would mark, it looks like it's going to be a in this case because a matches that same symbol. Sorry, I just covered it up. It's right here. I can't do an arrow, but you see it. It's right there. And I'm going to type 8 into the box right here. All right. Now, I'm not sure if it's going to ask you for the graph on the homework because I don't, it kind of puts the answers up one part at a time. So this is the only part that was available when I snapped the picture. There may be another part after this, but I know not every problem asks for interval notation, which I kind of don't like. I wish every problem was asking for interval notation in addition to graphing, in addition to solving it for x. I think all three parts are important and should be done every time. So I'm going to go ahead and do it. So even if your homework doesn't ask you to do it, I'm going to graph it and do the interval notation every time just so you can get a sense of how that works. So the graph for this, now if there is graphing on Math Excel, it's going to be multiple choice. They don't have a way for you to input the graph manually. So you'll have 4 choices. Just look very carefully, make sure you pick the right one. Here's 0 on the real number line, and then I look for 8 because that's the key number here. And then I decide, do I shade to the left or do I shade to the right? Well, less than, if I'm looking for numbers that are less than 8, those are the numbers that are to the left of 8. So here are all the numbers that are less than 8. They're all over here on the left-hand side of 8, forever to the left. And then because there's no equals to here, I will use a parentheses. So that's what the graph would look like. Now on Math Excel, if they do ask you to pick the right graph, they're going to give you 2 of them that go to the left, 2 of them that go to the right, and the difference between the 2 will be one has a parentheses and one has a bracket. So you have to look very carefully, make sure you're picking the graph going in the right direction with the right symbol on the number that you got in your inequality. All right. As an interval, again, we go from the very left to the very right, from smallest to largest. The smallest number in this region is negative infinity because it goes forever to the left. The largest number is 8. Always put parentheses on infinity, parentheses on the 8, just like we have in the graph. And so this is what the interval would look like. All right. We'll do the same thing here. We have 2y minus 1 is less than 4y minus 2. We're going to solve this for y. And for inequalities, you kind of want to keep the variable on the left-hand side. It makes it easier for graphing and for finding the interval notation. And so I'm going to move the y. I'm going to get rid of the y from the right-hand side, move it over here to the left-hand side. So I'm going to subtract 4y from both sides to get things started. And I'll get negative 2y minus 1 is less than negative 2. Don't forget that minus sign becomes a negative sign here. Then we'll add the 1 to both sides, so we get negative 2y is less than negative 1. And then to get y by itself, we'll divide by negative 2 on both sides. And I'll write the answer over here. We're going to get y is greater than 1/2. So kind of blew it there. By drawing it, I didn't draw it very well, but hopefully you caught that before I wrote it down, that it would have to become greater than, because this time we did divide by a negative on both sides of the inequality. And so that causes us to have to flip the inequality symbol around, because it's changing which one's bigger and which one's smaller, even though it's hard to see that's happening. The other thing I did, and I'm sorry if I did too much at once, but we had a -1 divided by -2, so that's a negative divided by a negative. So those negatives cancel each other out and become positive. And then 1/2 doesn't simplify or reduce, it just stays 1/2, it stays 1/2. And so that's how I came up with that answer. And so there is our solution to the inequality. Looks like this time the correct answer is D. Right? Got the greater than symbol there. Type in 1/2 into the box. This one I don't think they're going to ask you to graph because it has a fraction, but I'm going to go ahead and do it anyways. So we'll have 0, and then 1/2 will be just to the right of 0 because it's positive. Greater than 1/2, the numbers that are bigger than 1/2 are going to be to the right of 1/2. So it'll be all these numbers forever to the right. And again, parentheses on the 1/2 because there's no equals to over here. So this interval notation would go from the smallest number in the region, which is 1/2, comma, to the largest number, which is infinity. Parentheses always on infinity, parentheses on the 1/2, just like we have in the graph. So that's what the interval would look like, just in case it asks you to do that on the homework. Right. So this one's getting a little bit complicated, but it's not going to be too much more challenging. We just have to take our time to simplify it and be careful as we do, because we don't want to make any mistakes, because with Math Excel it's all or nothing. Either you get it right or you get it wrong. So we want to make sure we get it right so we can't make any mistakes. All right. So here is the expressions for the left and the right hand side. We have a greater than there. So just like we would for an equation, the only way we're going to be able to solve this for r is to get rid of the parentheses first. So that's what I'm going to do first. Distribute the 4 here. We get 4r minus 36. The plus 2 gets copied down. Here I'll distribute the 5, so I get 5r plus 15. The minus 23 gets copied down. Before I start moving things from one side of the inequality to the other, I simplify first by combining like terms. So I'll have 4r minus 34 here, right? We have negative 36 plus 2, that becomes negative 34. Here we combine these together, we'll have 5r minus 8. So 15 minus 23 would be negative 8. Again, I will move to have the variable on the left-hand side. I know with equations, if you watch my videos for section 1.1, I tried to avoid negative signs where I could. But for inequalities, if you have your variable on the right-hand side, it just makes it more difficult to figure out this solution. Students are more likely to make a mistake when the variable's on the right-hand side. So even though this is going to make a negative in front of our variable, it's better to have r on the right-hand side. Sorry, it's better to have r on the left-hand side. So let's go ahead and subtract the 5r over to the left-hand side. 4r minus 5r gives me negative 1r. Minus 34 is greater than negative 8. And then we will add 34 to the other side, and we get negative r is greater than, what is that going to be, 26. Kind of a big number. And then to get r by itself, because it's not quite isolated yet, we have to get rid of that negative sign. We'll divide by negative 1 on both sides. That'll make this positive r on the left-hand side, negative 26 on the right-hand side. And then because we divided by a negative on both sides, we have to flip the symbol the other way. And so we get this. And so the correct answer over here would be answer C, right? So again, all my examples here I picked do not have equals to in it, so maybe that was a bad choice on my part. But the graphing and the interval part is going to go much the same way as it did for the previous two problems. We have 0, negative 26, negative is going to be to the left of 0, so negative 26 will be kind of a long ways down here, but I'm just going to put it right there. Less than negative 26, the numbers less than negative 26 will be to the left of that. and then we use parentheses on the negative 26 because there's no equals to over here. The interval for this would go from negative infinity to negative 26. Parentheses on the infinity and parentheses on the negative 26 in this case. All right, I think this is my last example for the section. Finally, we have one with an equals to, so hopefully this one will work out nice. We do have some fractions to deal with, so let me talk about how we're going to do that. There's a couple things you could do. Now previously what we talked about when solving equations, to get rid of fractions, I said find the common denominator, multiply it to both sides. We could definitely do that here. But there is a little bit of a shortcut in this case. And this only works in this very particular situation when you have one fraction in front of x, and that's all you have, and you're trying to get x by itself, and you want to get rid of that one fraction. You can get rid of that one fraction all at once. You can do this in one step by multiplying by the reciprocal. So instead of doing common denominator, seeing what you get after that, then dividing by whatever to solve your inequality, you can just get x by itself all at once by multiplying by the reciprocal of this fraction. So the reciprocal of negative 7 over 4 is going to be negative 4 over 7. The sign will stay the same. So if I'm going to do that to the left-hand side to cancel out this fraction, I'm going to have to do the same thing to the right-hand side. Multiply by negative 4 over 7. So what's going to happen, what's nice about the reciprocal is that it just cancels everything out of that fraction, right? The 4 on top cancels out with the 4 on the bottom. The 7 on the bottom cancels out with the 7 on the top. Negative times a negative becomes positive. So those cancel each other out and everything's gone. And so we have x by itself. So it kind of takes care of everything all at once. On the right hand side, because we're multiplying here, so be careful about that, we don't need a common denominator. What we're going to do is try to reduce, and unfortunately it looks like this doesn't reduce very nicely. We do get a little bit canceling out here. So the 8 and the 4 can reduce with one another, right? By dividing a 4 out of both of those, we'll have a 1 left up here and a 2 left down here. And I think that's all we're going to be able to do. Negative times a negative makes this positive, and so we'll go ahead and multiply. So 9 times 1 gives me 9 on top. 2 times 7 gives me 14 on the bottom, and it'll be positive. And the reason I put this problem on here, and the reason I want to do the problem in this particular way, is to remind you of something that doesn't happen as often, but it's still important for you to remember. If you multiply by a negative on both sides of your inequality, you have to flip the symbol around. So 95% of the time, you're flipping the symbol around because you're dividing by a negative on both sides. That's just how the problems are typically set up for that to happen. But it's still true that if you multiply by a negative on both sides, the rule is still in effect. You have to flip the symbol around. And so be careful about that. All right, and so this would be the final answer here, which means I'd want to select option A. 9 over 14 goes in the box there. I'll graph it. So again, because it's positive, it'll be to the right of 0. I'm looking for numbers that are less than 9 over 14. Those will be all the numbers to the left of 9 over 14. Those are the numbers that are less than. This time, because we do have an equals to, we will use a bracket on the 9 over 14. Sorry, it's a little bit off the mark, but you get the idea. So that should be on the number 9 over 14. And then as an interval, smallest to largest, we're going to go from negative infinity, comma, up to 9 over 14. Always put parentheses on the infinity, but this time the 9 over 14 gets a bracket because of the equals to. And so that's what the interval would look like. All right, so this has been section 1.4 on inequalities. The next section we'll look at, section 1.5, we're going to be looking at some more inequalities, but they will be compound inequalities. So they're going to be a little bit more challenging. So I'll see you for the next video.